Jackson. Now, you go ahead.
Since the late 50s, NASA has been the leader in ion technology. The 1998 Deep Space One probe truly showed the potential of ion technology when it traveled over 163 million miles, propelled primarily by an ion engine. In 2007, the Dawn spacecraft launched and proved once again the success of the ion engine. As an aerospace engineer, I'm interested in all aspects of space travel. I want to ensure the safety and protection of our astronauts on board, minimize costs, lengthen the operational life of our satellites, etc. With this, I propose we continue our investment in engine designs that utilize ion technology and broaden it into every spacecraft. I'll first talk about factors that affect our ability to space travel, including time and fuel capacity. Afterwards, I'll talk about how our current use of chemical rockets are inefficient. And lastly, I'll provide a solution that hopefully convinces you that ion technology is the future. Starting off, the biggest problem facing our ability for long-distance space travel is a combination of long travel time and limited fuel. The most pressing issue that most mission coordinators have to face is how effectively can they utilize the limited amount of liquid fuel they have on a mission. On chapter 13 in the textbook Basics of Spaceflight by David Duty 2011, whenever a spacecraft wishes to make a maneuver, a value called delta V is created to put the spacecraft on course. In the simplest terms, delta V is the amount of thrust and velocity required to perform a maneuver. Delta Vs are utilized primarily because it's a good strategy to minimize fuel consumption. Once a spacecraft initiates a burn with the right delta V, it will coast through space until it needs to make its next maneuver. Now, this strategy seems to work fine. NASA has been using it for decades. But the time it takes to coast after a maneuver is time consuming. There isn't a constant acceleration that propels the spacecraft forward. It only just drifts through space. So far, I've told you the strategy of our current system, but all of this is based on the use of chemical rockets for space travel. For decades, chemical rockets have been the foundation of spaceflight, but in interplanetary space, they are fundamentally limited by their fuel capacity and weight. According to an article published by NASA, written by flight engineer Dawn Petit 2012, upwards of at least 85% of a rocket's mass before takeoff is made up of fuel. From one aspect, the excess weight of fuel prevents what we can bring into space. But in another aspect, the limited fuel capacity shrinks the operational life of most spacecraft. With all that said, there are no other options that exist that can produce enough thrust for takeoff than chemical rockets. Chemical rockets should still be used for initial takeoff, but for interplanetary space, they should and can be replaced. We need chemical rockets to launch from Earth, but what we can do is implement ion thrusters for in-space propulsion. Ion thrusters are highly efficient, low-thrust propulsion systems that run on electrical power and can provide long, continuous burns. According to an article by Martinez Sanchez in 1998, published by the Journal of Propulsion and Power, the basic premise of an ion thruster is that ions, or charged atoms, are produced in a chamber by bombarding electrons into some neutral gas, usually just xenon. The positive atoms are then extracted and accelerated through charged grid systems that contain these very small holes. This generates thrust as the particles move through the potential difference of the grids. The key behind ion thrusters is that they can provide continuous thrust that builds up throughout the journey. This can greatly reduce the time and complexity of missions. Because of the continuous burn, spacecraft powered by thrusters can reach speeds up to 200,000 miles per hour. For comparison, the space shuttles reached only around 18,000 miles per hour. The trade-off with high speeds and high efficiency, however, is low acceleration. Current ion thrusters provide only 1/10 of a pound of force, equivalent of holding about 10 quarters in your hand. This means ion thrusters won't launch spacecraft into space anytime soon, but they are capable in space to reach incredibly fast speeds and be fuel efficient. Ion propulsion is a proven and reliable system that, despite low acceleration, is fuel efficient and can propel a spacecraft to incredible speeds. I've told you the problems we face with our current system, with chemical rockets, and how ion propulsion can be used as an eventual replacement. I want to reiterate how important it is that we continue to invest in ion technology and eventually replace all in-space engines with ion engines. To quote Buzz Aldrin, space is not just going up and coming back down again. Space is getting into orbit and being there, living there, establishing a presence, a permanence. Ion propulsion become a permanent part of this vision. Thank you very much.
All right.
All right,
Corey
very
Fair,
good.
Jason. Corey Fair.
Bravo, take a
That
bow.
was 6 minutes and 3 seconds.
Perfect.
That shows you how, when you get it down, that's